How do I?
Okay. Alrighty. Bear with it, guys. I'm trying to share my screen. And we practiced before, and
Ray, I
it's
think
not
you need
doing
to
the way I
stop
wanted
sharing.
it. Oh well. I'm gonna have to do it in 2 phases. I was hoping to make it more seamless. So look, when you guys think about lakes, well, actually we have some folks here who haven't started to work on lakes, and we have some who've probably worked on lakes longer than I have. But you know, if you just look out at a lake, you know, and it's a calm day, that surface is so very, very flat. And you think, not much goes on here. There's probably some cool fish, maybe some really neat benthic invertebrates. Maybe there's an algal bloom, and maybe it smells or maybe it doesn't, or maybe the water is really clear and you want to go for a swim. But a lot of times you don't really think about what goes on below the surface. So I want to just start by showing a three-dimensional movie based on a 3D model, with this model done by Ben Hodges on Lake Kinneret. And it isn't really where I wanted to start. It's just that my PowerPoints don't always accept my movies anymore. And I know for some of you that all the terminology is brand new, and for others it's well known. But when we look at this movie, right up here, well, each of these lines is a line of constant temperature. And so where they're really far apart, that's our upper mixed layer. Where they're close together, that's a thermocline. And then down there where they're a little wider, it's the hypolimnion or deep water. Now, Lake Kinneret is about 150 square kilometers. I forgot to check how deep it is, but I think it's around 25 meters. And I even forgot to check how broad it is, but 150 square kilometers might be 20 kilometers long. Almost every day, the wind will come from the Mediterranean Ocean across Lake Kinneret. And what we're going to see is what that wind does to the thermocline in the mixed layer. So there's a scale bar here. This little arrow means a 10 meter per second wind, and this little one right here is going to change magnitude, and you'll see how windy it is. And then the velocities like this are the horizontal current speeds, and the ones in this direction are actually the velocity of the vertical movement of the isotherms. Okay? And this upper little panel right here shows the percentage of the water column that's actually mixing. So if a whole lot of it's mixing, it's red, and if not much at all is mixing, it's blue. Okay, so I'm going to start this movie in just a second. Oh, one thing, if you guys have questions, be sure to put something in the chat, and Freya and Todd are going to monitor that, and they'll try to slow me down. I can see them. And say, hey, Sally, you got a question. Okay, because if something's really unclear, you know, just get it out there. Or if I ask you a question, be nice to know your answer. Okay, so here we go. And the first thing you notice is the thermocline is not stable. So think about how if you look at a picture in a book, you see that thermocline is a fixed depth. You know, it's not stable at all. And when that wind gets blowing, like right there, see how it got pushed down over on the eastern side of the lake. And I'm going to try to stop at that next time. When that wind really blew, okay, so this is when the wind is strongest coming across the country of Israel. See how the mixed layer deepened over on the one side? See how it got really compressed on the other? And the thermocline, you know, because sometimes you might run a computer package and you go, what's the depth of the thermocline? And you have your one set of data that's from one location, and you go, well, the thermocline got really deep. Man, it went down to 10 meters. Well, guess what? It's over here, 2 meters over there. So a thermocline is not just a fixed entity, just sitting there, kind of maybe at the most, you know, it rocks back and forth. Now, another thing that often we see, that here the isotherms are compressed. Here you can see they're kind of spread out. While that wind was blowing, this whole upper mixed layer is actually, in theory, mixed. And it's going to have a flow structure kind of like this, going across and down and back around. And then the hypolimnetic water. Look how high that hypolimnetic water came. And there's little patches indicating mixing here. And so, of course, a question we might be interested in is, if the hypolimnetic water is anoxic, does any exchange occur up here? Maybe you would put, and if it's anoxic, most of us know there's probably more phosphorus or methane. And maybe it's going to push some of it in here because there'll be a mixing event. But anyhow, then the wind is going to relax. And then you see how the thermocline there, whoops, I tried to stop it. So then when the wind relaxed, see what's going to happen. We've got a little motion here, but this is going to upwell on this side, and this other water is going to flow back here across the lake. Okay. With this movie, I never can guarantee when I'll stop anything. And here's another example. Fully depressed, isotherms have upwelled. Here they upwelled even more. So some of the thermocline water reached the surface. And then lo and behold, now it's 10 o'clock at night, and now it looks kind of like that quiet lake, that you thought about before. And it says none of the mixed layers mixing, and the thermocline is level once again. Okay, so anyhow, the bottom line here is that lakes are really dynamic systems. And what I want to do in this lecture is give you kind of a sense about how those dynamic, as I go back into sharing again, just kind of there we go, we got my talk. The dynamics of that mixing and what we've been learning, since the time that Hutchinson came up with the first classification scheme till today, okay? How's that? Can you see this first slide? Okay, cool. So look, I always like pretty pictures, and I didn't put enough in, but at least we have one. And this is a picture up in the Arctic where I work. This is Toolik Lake. I'm going to have some data from there. And it's the Brooks Range to the background. The photograph is probably July because we have intermittent snowstorms in the summer. And the Arctic Ocean is probably about 250 kilometers to the north of where we took this picture. And there's a whole lot I'd like to say about this, but I won't in the interest of finishing the talk. Okay, so why do we care about mixing dynamics? Well, first off, they create the structure in the water column that provides the habitat for organisms. And you saw that mixed layer in Lake Kinneret, and it was probably 5 to 7 meters deep. And if there's phytoplankton there, you saw part of the day they're mixing and part of the day they're not. Okay, and that was just one movie at one period of time. And maybe the next week the wind didn't blow, but that's actually not what happens in that area. I think it blows pretty much every day. But that mixing is really important because it determines the outcome of competition between species. Like we often think that the cyanobacteria prefer quiet, more quiescent conditions. And we know that diatoms, for instance, want to have a more turbulent water column because it helps them stay in suspension. So how much that water column is mixing might determine whether or not you have a diatom-dominated community or a cyanobacterial-dominated community. And then, of course, there's some of those phytoplankton that can swim, and they may be the ones who do really well also in a quiet water column where they can swim up to the light or they can swim down to where the nutrients are located. So that's real, that's about competition and habitat. Resource supply. Later I'll show you another picture, but most of us already think that the hypolimnion is a source of nutrients. And so if we can mix water from the deeper parts of the lake up in the upper mixed layer, it might initiate a bloom. Now, of course, the same is true if a stream comes in with nutrients, there you go. But also, a lot of us are interested in the question of fluxes of greenhouse gases. And that mixing then is very important. Do we deepen the mixed layer and do we bring up any CO2 or methane that are sequestered at depth? And then the mixing near the surface, that near surface turbulence, is determining the gas transfer velocity that lets those gases go across the air-water interface. So I wanted to start with this phase diagram here. It was initiated by Hutchinson, and then in about probably 1957, and then it was modified in this form by Bill Lewis. And I put it here because we're thinking, what's this talk to do with Hutchinson? Okay, and we've got these various classification schemes, many of which you are already familiar. And for some of you, this is the first time you've ever heard these words. But the whole point of a phase diagram, one, is the kind of tool that physical limnologists use a lot, and there's no reason a biological, and I know chemical oceanographers do as well. But what we do is we have, on one axis is latitude, and here's the tropics, and this could be going north or south from the equator. And then we have lake depth. And many of you working in the northern temperate zone work in lakes that are dimictic. Okay, so the phase diagram here of Hutchinson and Lewis is thinking about the annual mixing patterns. And dimictic means it's going to mix twice a year. And some of you are working in locations further to the south, and the lakes don't freeze in the winter. And so then, they stratify more in the summer, and then they have a winter period of mixing. And then if you're working in a shallower lake, you might actually find that in that period when the dimictic lake or the warm monomictic lake was stratifying, that in fact, it'll mix to the bottom, the polymictic lake will mix to the bottom, re-stratify, mix to the bottom, and re-stratify quite frequently. The point here is, you guys, most of you know these terms, but this is the kind of tool that I'm going to show you that we physical limnologists use a lot, and they give us a lot of predictive power. Okay. So reading this, so their schemes indicate how frequently lakes mix throughout the water column annually. And these patterns set the template for the growth of organisms. However, we need to know when and where mixing, that is the turbulence, occurs during the stratified periods in order to understand what resources apply to organisms, conditions conducive to hypoxia, and we want to know how patterns of mixing will change over time so we can anticipate the future health and productivity of our lakes. And in this talk, I would love to have time to cite some of the really great collaborative recent GLION papers. And I just don't have time to include all the references. I can see the co-authors' names, as I have that slide, but I'm not going to go there. It would take too much time. But the other thing, in preparing this talk, I reflected back on what it was like when I was a graduate student. And I was actually very fortunate because I had 2 years working on lakes in Africa as a technician, and then I started graduate school. And of course, right away, I took a class, and right away, I had to give an oral presentation. And the paper that I selected to read, because while in Africa, I decided to study turbulence, not really realizing how difficult a field it was. But that first paper was this one by Clifford Mortimer called Lake Hydrodynamics. And I'm mentioning it in part to give you guys a sense of maybe confidence. What I was able to do, it took me 5 times reading it before I began to understand what Clifford Mortimer was talking about. And on top of that, I only got that far. So the first 25 pages. So I want you to think when you're reading the primary literature that you may not get it the first time, but just keep staying with it. Another little thing is, the whole first page didn't show, but a general introduction list of topics here neglected. Well, I have a lot of topics I'm neglecting too. But there's another little story about this, and that is when I gave the talk on this paper, I debated also probably for 5 days whether or not I would put a certain set of equations on the blackboard. We weren't doing PowerPoint talks back then. And once I did it, the instructor went, Eric, I'm not brave enough to put out a really big screech right now, but it was quite the screech, you know, and it had taken me so much boldness to put this up that his screech just basically terrified me. Well, I want you to know that it took me to being a faculty member myself to realize that sometimes when a faculty member makes a loud noise like that, it's not because they think you've done something really stupid or bad. It's because maybe they learned something, or maybe you've shown something really cool. So anyhow, have confidence and don't necessarily take too seriously the emotional outbursts of your colleagues. And another little comment I wanted to make about graduate school before I get too far along is don't get too discouraged with the first reviews of your papers. And I was thinking it might have been gentler times back when I submitted my first one or ones, but I remember on the second that the editor-in-chief wrote, "If I didn't know this author, I would have thought this would be impossible to revise. But I do think there's some hope." So it was one of those backhanded compliments. And the bottom line was my early papers and even some of my recent ones suffer from being a little confusing. And so I want you all to know that when you get those reviews back, and maybe they don't have backhanded compliments that are motivating, but that's the name of the game. And you're actually really lucky when people give you good feedback. And don't worry about it. And I was really, really impressed with one graduate student. She wasn't mine, but she was one with whom I was working. And I hadn't learned, I wasn't far enough along to know that I should really give her a lot of feedback on that paper. You know, I did on some of the quantitative stuff, but not as much on the writing. And now I do give more. Anyhow, that paper got rejected, but the reviewers gave her a whole lot of guidelines on how to revise her paper. And so she said, "Oh, they gave me these guidelines. I revised it. I submitted it somewhere else." And lo and behold, it got accepted. So even if you have that bad luck of an actual rejection, just carry on. And you know, those are just a few comments I wanted to make for you, recalling my own graduate student school experiences as well as the challenge of getting papers published. Okay, so as a guide to these two lectures, so CLAM was established as we began to recognize the value of high-frequency data, meaning a lot of thermistors in a lake, to study lakes. An initial goal was to quantify lake metabolism. And I don't know how many of you are actually doing lake metabolism, but I think it's actually the most difficult physical limnological problem. So just to give you a sense that this is really non-trivial. But I've also noted from seeing all the various projects that get put forward that the range has extended considerably. But what I'm doing here is providing background on the field of physical limnology. And the first part kind of summarizes what we've learned in the last couple of decades about processes influencing vertical exchange, that is turbulence, which is key for resource supply for the plankton and for computing metabolism. But we also need to be thinking about horizontal exchange to compute metabolism correctly or to address problems such as, now I put this one here when I looked at the list of participants, because I know somebody in the audience is really interested in this problem. Are mid-lake fluxes of methane due to oxic production or transport of methane produced in the sediments near shore? Okay, so I can't do justice to that kind of question in this talk, okay? And another one, again, thinking about who's coming, we also have incoming streams and rivers. So I really can't do those topics fully in these two talks, but I've included some movies and with an idea so you'll get a sense of spatial variability and you can begin to develop approaches to scale those processes. Okay, turbulent eddies. I actually have movies that go with this, and again, they didn't mount very well, so I'm not going to show them. But when you have turbulent motions, they're three-dimensional. And, you know, here's one turbulent eddy, and you can see how everything is curled up inside. And then here's another turbulent eddy, and then there's smaller eddies inside of it, and there's even smaller eddies inside here. And the poem from Richardson is, big whirls have little whirls with lesser whirls inside them. Oh, I've got it wrong. And little whirls have smaller whirls, and so on to viscosity. I didn't get it right. Sometimes I try to do it by memory. But anyhow, the fluid is really, really being stretched. Smaller eddies get generated, and eventually the eddies get so small that molecular diffusion can occur from this region of high concentration over to the region where there's not much. Now, if you were to look at like some satellite pictures on the ocean, you could see some really, really big eddies. So really huge. And we can think of the mixed layer. When it's mixing, the whole depth can be one really large eddy. When we get in the stratified parts of the lake, those eddies may only be 20 centimeters, but then you have a cascade down to smaller sizes. But they're really important for circulating the phytoplankton, the zooplankton, and their size and frequency in the water determine what we call the upper mixed layer, where there's a whole lot more of these eddies, the thermocline, where there are fewer and usually smaller, in the hypolimnion. And again, just so you can think about like the difficulty of a zooplankton catching a phytoplankton, imagine that the zooplankton was here and the phytoplankton was there, and that zooplankton thought they could swim to here and get that phytoplankton. But then the eddy swept them right there, and it swept the phytoplankton cell over there. That actually all happens on the size scale of those organisms and adds to the complexity of living in a turbulent environment. Okay, so in aquatic ecosystem studies, the hydrodynamics allows us to compute fluxes. So I've got a real simple picture of a lake here, and we have a temperature profile. And again, that upper mixed layer, the thermocline, the hypolimnion. And our normal model of a lake is that there's light up here, and there's nutrients here, and there's dissolved gases here. And we often think that the phytoplankton don't have enough nutrients. So we want to know how much mixing there is that would bring those nutrients up where the light is, and maybe there's more phytoplankton. And remember, this is a simple model, just to give you a sense of how things work. We also might really care about the gas fluxes, and we want to know what's that mixing like that's bringing the methane and the CO2 in the upper water column, where then they can go across the air-water interface. And we usually characterize the mixing with the coefficient of eddy diffusivity. And that lets us calculate the flux, right? That mass or those moles per meter squared per unit time. And like many equations in physical limnology, it's deceptively simple because it's just Kz times the concentration gradient. Notice also the arrow for advection, which I can't do justice to. And yeah, here I put oxygen, and I didn't put an oxy down there, but we know that may be what it's like. And this might be your profile of light, or it might be a temperature profile on a day where there hadn't been much wind and there was a lot of near surface stratification. But there's another K that we really like to get in physical limnology. And unfortunately, I'm not going to do justice to it today. But again, this one is flux times this K times the concentration gradient here in the water and then up at the very surface of this diffusive boundary layer. And I won't do more details with that. And all I can tell for those people here, I saw Meredith was here, all those people here who care about gas transfer, a paper that I've been working on diligently for many years is down to the last wire, and hopefully one more revision and it'll come out. And it's got some new ways to think about K, but I don't have time to talk about it here. Okay, so how does the field of physical limnology advance? Like, what do we really do? Well, we conduct laboratory and field experiments to identify processes. We develop and we solve equations describing those processes. We develop dimensionless indices, meaning little indices that have no units. All the significant variables are put in and the units are all designed to cancel. And phase diagrams like the one I showed you from Hutchinson and Lewis. And then we apply these in the field to understand lakes as a whole and the relation of hydrodynamics to biogeochemistry and biology. And I know many of you have started to do that with your work. Now, what kind of measurements do? We measure meteorology, so that's wind and humidity and long and shortwave radiation, air temperature, the intensity of rain. We do time series measurements of temperature, specific conductance, and oxygen. We measure the velocity of the water using acoustic Doppler current profilers. And for turbulence, we may use a temperature gradient microstructure profiler like this SCAMP. We may use acoustic Doppler velocimeters, the new acoustic Doppler current profilers, the signature 1000s. And nowadays, we even put the fast response sensors, like here on my profiler, onto gliders in autonomous underwater vehicles. So just to keep things light, I had to show at least a few pictures of people in the field. So here we are installing a met station on an embayment of a lake in the Amazon River. And of course, you can see the anemometer, the air temperature, relative humidity, direction, rain gauges. But one thing, some of you might, you might hear about expensive systems that you can buy that somebody's already put together. But a lot of times when we work, we just, we build our own platform. This was built in somebody's garage. This is an onset met station, which are really great for portable field work. We've also tried the gill ones, and these are your lower cost ones, but they're perfect because you can get them right out there where you're working. And what techniques do we use to characterize stratification? Well, we use moored arrays with temperature, conductivity, and oxygen sensors. And this one's just to give you kind of a sense of what things look like coming back from the field. But in the wintertime, we use the double buoys. Here's one of my temperature sensors. But I put this in so nowadays it's not just temperature. You're also trying to get oxygen, conductivity, pressure, because we have so many more of these. In fact, back for my thesis, I built current meters, and then on my next project, I was building thermistor arrays from scratch. We could buy a data logger, but I had to put all the things together. Things have come a long way. And then returning from the field after pulling up the winter array. And here's just another picture of my SCAMP. We all know that we profile on lakes, and you may use a simple YSI temperature oxygen profiler. You might use a hydrolab. You might have a YSI instrument. And mine is the one made by Mike Head, the one who makes the mini dots that some of you are familiar with. It is a conductivity temperature depth profiler, but this one also does turbulence. So there's what it does. And also, for instance, I put in a schematic of our taut line mooring design. And I did this, first off, of course, we don't have thermistors horizontal. They're really vertical. And the artist just thought it was easy to put them horizontal, but they're all vertical. And of course, we don't only have thermistors, we do have the oxygen and the specific conductivity sensors. But we use the taut line array, so there's a weight at the bottom, and then it goes up to a buoy that holds everything tight. That's why it's called a taut line array. But the other thing that I do, and it took me a while to come up with this design, is I have a little surface float like this, and right on the very bottom of it, and this time it is horizontal, is my top thermistor. And then, of course, I'll usually have a couple others that are dangling down, and then they're held down by a weight, and then we connect over to our other buoy. I mentioned this, like in this talk, I really can't do justice to surface energy budgets, calculating latent and sensible heat exchange. But when you really want to be knowing, when you have those really important calculations that really allow you to do mixed layer dynamics, you need to have a measurement of temperature at the very surface. So this lets you have a float that shields your thermistor, and mine are, the way the float works, my surface measurement is usually within 2 or 5 centimeters of the air-water interface. And this is a sketch made by a postdoc a number of years ago. And again, I can't go into all the details of the measurements, but what sets up our circulation patterns. Short wave coming in that stratifies. Latent heat fluxes, which is usually a heat loss term. Sensible, which could go either way. The long wave radiation. Working together, these processes determine, is that water column stratified? Is it not? If there's not much sunlight, we may have convective cooling, and we may have large eddies that are mixing the whole thermocline. When the wind blows, we're going to set up currents. And when Ted drew this picture, he put a whole lot of shear in, suggesting the wind would mix that mixed layer. And as the wind blows like this, we tilt the thermocline, as you saw in Ben Hodges' movie. Okay, so now this is a figure made by Mortimer. And I do love this picture. And notice it's Windermere, the North Basin. And one of the things the older scientists, it is incredible to realize everything that they figured out with instrumentation, which is so much cruder than what we have today. Really amazing. But this sketch really shows you everything that was in Ben Hodges' movie. And how did Clifford figure this out? He would have done transects all the way along Lake Windermere. All those profiles. He didn't have a scamp. He probably had a pretty slow instrument. But he got the profiles, and then he could say, here's my mixed layer, here's my thermocline, here's the hypolimnion. The wind blew, it set the surface moving, and we have a return flow, and it initiates flow in the hypolimnion. As the wind continues, that mixed layer downwells over on one side. But what's real important here is the wind is blown enough that the hypolimnion has reached the surface. And as you'll see in a little bit, that's a setup then for a Wedderburn number that's less than 1. Okay, and we'll get to that. And then it keeps blowing. And also we put these little eddies in. And I'm not going to give you guys definitions of Kelvin-Helmholtz billows, but they're indicative of all the shear between that mixed layer and the deeper water. And then he finally shows you what the temperature distribution looked like at the end of that event. But I also like the fact that what you see here is this is where the thermocline started, and notice it's deeper, okay? And we're going to see why the thermocline can deepen after a strong wind event. But I really, normally I would go through this picture and then show the movie. But like I said, I couldn't. But again, it gives you that sense that lakes are really dynamic. Okay, now we went through instrumentation, and I did keep this one in, again, because there's some folks here who've never looked at a time depth diagram before. And this would be one of Bob Wetzel. And also, the reason I put it in is the next few slides are going to show you data from some dimictic lakes, from some warm monomictic lakes, and from some polymictic lakes. And some are Arctic and some are tropical, so you can see some differences. But because Wetzel's got a whole year showing, we can now look at what a dimictic lake really looks like. So the y-axis is depth, and the x-axis is all the months of a year. The black here means there's ice, so it kind of melted away towards the end of March. And then the ice reformed around December. Every one of these lines is a line of constant temperature. So what you see is under the ice, the coldest water is near the surface and the warmest is at the bottom. And then after ice off, a lot of the water column is around 4 degrees, which is the temperature of maximum density. And then the contours are all real close together, telling you that the lake is heating. And then it doesn't heat as fast. And then it reaches its maximum of 25 degrees. And then when the isotherms rise, that's telling you that the water body is cooling. And here we can see that it mixed, and we've got 5-degree water. And then once again, underneath the ice, we have what we call inverse temperature stratification, but it's still stable, right? This warmer water is less dense than the colder water. So this is a stable stratification. Here it's isothermal, and here it's stable again because 1-degree water is less dense than 4-degree water. Does anybody have any questions on that? I figure most of you are familiar, but I needed to review for the few who haven't worked with time depth diagrams before. But now, here's a graph that just shows you how much more information we get when we have the high frequency sensors. And again, thinking about this, you'll notice the date of this, 1999. And if you count the number of little stars over here on the side, you can see how many temperature loggers I owned at that time. It looks like 9. And to give you a sense also of how difficult things are, the data set is patched together because the memory wasn't very long in those first ones. And now you all know you could probably sample for 10 seconds for 3 years with some of the new instruments, but we couldn't in the past. But once we have this data, you see the heating period, it cooled, it heated, we had a cooling period, and it got colder, and then it warmed up again. But the lake stayed stratified this whole time. Ice off was over here, and this is sort of the end of August right there, and then it's going to cool and the ice will form. It's a dimictic lake in the Arctic. The thermocline, there's always a lot of discussion. What's a thermocline? Most strongly stratified region, right? We could define that. But we also could say, what's the metalimnion? And that's where a lot of the water column is stratified. And here it's from 3 to about 8 meters. Now I want you to look at this graph and see if you can see any other features. Okay, I didn't make one of those question and answer things. Can you see any evidence of diurnal thermoclines, right? That heating in the day because it wasn't windy, and then that heating went away. Can you see any evidence that there was a really big rainstorm and then an intrusion? There's one big stream that comes into Tulip Lake. Can you see any evidence that a stream came into that lake and it might have brought in CO2, probably not methane, probably a bunch of DOC, maybe it brought in nutrients? And can you see any evidence of the kind of change in depth of the thermocline that we could just see in that illustration that Mortimer had made? Now I can't look, I don't know if anybody's willing to raise their hand and make a guess.
There was a question in the chat, Sally, about what do the red dots indicate?
Oh, the red dots are the depths where we had the thermistors. And you'll notice that they're not evenly spaced, right? They're a lot closer together in the mixed layer and they're further apart. Also, because I didn't have very many in the beginning, I didn't instrument the hole to the bottom of the lake, which is about 24 meters. In later years, I had more instruments and could do it. But one of the things you notice, so this is an example here, this shows you the diurnal thermoclines, right, forming every day. You notice that this mixed layer, especially after ice off, is not very deep. It's only about 2.5 meters. And then over here, it's 5. And if you look at maybe some of your time series data from bigger lakes, you might go, wow, these are really shallow upper mixed layers. This lake is 1.5 kilometers squared. It's really a small lake, but for some of you who study ponds, it's a big lake, right? We always have a little problem with that. But anyhow, the stream, this is the stream coming in. And again, it takes time to train your eyes to see things like that. I didn't probably see that for 1 or 2 years after collecting this data, and now I can see that anytime I look at data, I go, oh, look, these isotherms separated in the middle of the thermocline. That probably means there was a rainstorm. And in fact, no, I won't get into that story. And the other unusual thing right here is this jump, okay? And that is the case where the wind was so very, very strong, it caused really intense mixing. And again, going back to like when you present material, I showed this slide in the seminar back at the Center for Water Research in Australia, and Jörg Imberger went, Sally, that's a hydraulic jump. Oh no, Jörg, surely it's not. Well, it was, and I didn't know enough then, okay? And we will get to what causes this sort of feature, but it can cause a huge amount of transport between the hypolimnion and the mixed layer, just as you could see in Mortimer's sketch, when in fact, if we'd had thermistors all the way along the lake, we would have seen that upwelling of the hypolimnetic water reaching the surface, and then hypolimnetic water went up and epilimnetic water went down, And so this feature deepened, and down here actually got warmer. Okay. Now I put this in because some of you are interested in winter limnology, and you know, when you think about the graph that Wetzel made, and you saw winter, you just saw colder temperatures near the top, and you saw warmer at the bottom. All right, so my color bar in this figure is going from 1 to about just over about 4 degrees. We're starting in about September of 2013, and the data is continuing into June of 2014. And you look at this, and you can see, wow, there's even internal waves underneath the ice, right? And we'll get more into what internal waves are later. And then you could look at what goes on at fall cooling, because the old idea was as soon as the temperatures reached 4 degrees, it was denser and the whole water column would mix and it would be isothermal. And what's really happening here, these up and downs, that's the whole thermocline in the lake doing all this type of back and forth motion. So it's a lot of huge upwelling. And then when the ice went on, in fact, the water column wasn't fully mixed, okay? And then another really big surprise for us was, you know, again, the old idea was that as soon as spring came along and your temperatures reached 4 degrees, the water would be denser at the surface and it would mix the whole water column. And what you see is the water column actually didn't mix completely. And that means there can be a lot of dissolved gases. You know, if you're interested in the amount of CO2 or methane that's produced over the winter, or if you were working in a lake that had become anoxic, that means that those conditions remain in the lower water column, and they set the stage for a lot of different differences in the summer. Okay, I'm watching our time, and you know, and I decided to take the time to go over these graphs. And I think we'll just get through this one series before we you know, call it a day. Here's some data from a reservoir in Brazil. So now we're in the tropics. I'm only showing you what, 5.5 days of data. And what do you see that looks really different here? One, the temperatures, right? 32 degrees to 28. And for those of us who only think in Fahrenheit, that's in the 80s. And the lake, these lakes are usually too hot to swim in around noon. And you usually wait till it's approaching sundown because that intense solar radiation plus warm water doesn't really feel good. But here we have an upper water column, and here's the thermocline. You know, when we look at the thermocline, we can see it's active, right? These are nonlinear internal waves, and it's pretty strongly stratified. And in fact, the lake is anoxic right here. But in this graph, you can see so very, very well the formation of what we call a diurnal thermocline, which I just hinted at in the figure from Tulik. And if we follow these contours, right, that diurnal thermocline is setting up, well, initially right at the surface, and here it is at a meter. And then when the wind comes up, it pushes down, but then it's kind of strange because look, the diurnal thermocline rises. You know, you would think, remember, this is midnight, and this is midnight, and here's noon. So you would think in the middle of the day, right, it's still warm. Why would a diurnal thermocline rise? That's kind of crazy, okay? Now, another thing we can say is when we looked at the data from Tulik, the depth of the upper mixed layer was only about 3 meters. And, well, the air temperatures there, well, they're not as hot as in the tropics, but it's still a really shallow mixed layer. Here we could say, well, the upper mixed layer is probably 15 meters deep, okay? So we have this diurnal thermocline, and below it, a region we call a subsurface layer. Again, for those who are interested in gas transfer, the crazy thing is the gas exchange coefficients are highest here when it's most stratified. It's really amazing, not when it's cooling. But if you were thinking, when do we entrain some extra nutrients or gases? Those few nights when the convective cooling was appreciable enough, we could bring up those gases. But the issue then, I want to just, I threw this other figure in right before starting. And this one, here we've got fairly closely spaced isotherms. And now I've drawn some that are probably the 0.005 degree interval. And when you look at this, you notice there's an internal wave motion. Okay, it breaks with the convection. So we have the diurnal thermocline here, but below in the subsurface layer, it's not static either. It's actually supporting an internal wave field. And this wave field, in fact, is a whole lot like what we just saw for Lake Kinneret. There, they tilted the thermocline like this, and then it went back. So Balbina Reservoir has the same type of tilting. The wind is one direction from the morning until about 2 to 3 in the afternoon, and then it shifts direction. And so this diurnal thermocline that went down when the wind first came up, now it's reversing because it's part of a much bigger internal wave field that's filling this whole lake. You just don't think about things like this. Anyhow, I wouldn't have. Okay, now I'm showing you. Okay, so again on this theme, Balbina is a warm monomictic lake. Okay, now I've never seen any data when it's fully mixed, but it's in a location where there ought to be a period of time when it's cool enough to mix to the bottom. But now I'm showing you some data from Lago Janawaca, which is a lake along the Amazon at low water. And at this low water stage, the lake is polymictic. So now we only have a 2-meter deep lake. And here's the time series of temperatures. And we can see, wow, it really, really stratifies near the top. The attenuation coefficient here is 2. For Balbina, it was 0.5, for those of you who know those numbers. And for Tulik, it's about 0.6. So you can see this amazing near-surface stratification. The wind comes up, the diurnal thermocline goes down, we have some nocturnal cooling. But what? It got warmer. And then we continue to cool, and it sets up the next day. But a really important thing to realize is that temperatures can go isothermal, or you could do what I did in that last slide. You can move down so you're resolving the temperature differences to smaller and smaller increments, and maybe you can see some residual stratification. But a lot of times when you're measuring scalars, the scalars don't mix anywhere near as fast as the temperature does. You can see a whole lot more structure. Now again, talking this through, it's only 2 days of data. We expect photosynthesis to be high in the morning with all the bright sun, and we expect it to continue reasonably into the afternoon. So here we have high oxygen, and as that diurnal thermocline descends, it's being mixed through more of the water column. And now you know at night, right, and so sunset's going to be right about there, respiration is going to dominate. But remember, we're also exchanging the oxygen with the atmosphere. But what else do we see? Well, in fact, we can see a cold water intrusion at the bottom, a deoxygenated intrusion, well, more like hypoxic intrusion at the bottom. So there was an internal wave. And then we can go, well, look, it's sunset and there's more oxygen. Why is that? And this is, I wanted to mention this because we're people interested in like that oxic methane production and nearshore transport. And if you're measuring metabolism at one location, how representative is it of the whole lake? Well, you can see that if you start to get an intrusion of oxygenated water at sunset, you know it flowed from somewhere else. So there's a lot of advection in the system. Okay, so I'm watching our time. So when we think about Hutchinson's and Lewis's schemes, they provide an annual classification. But to study ecosystems, we need to know how frequently the vertical mixing occurs in the stratified periods. Can we predict the depths over which water is exchanged? Can we predict the coefficient of eddy diffusivity? And is there horizontal exchange? And I think I'm going to try to stop, but I just want to see what the next slide is. Yeah, okay, so that's a good break point because starting tomorrow, then we'll get more into internal waves and the relation to turbulence and some of the experiments that were critical, what the waves are like, and then how we can see how really different then the turbulence might be in a temperate lake versus an Arctic lake of the same size. And then in an Arctic region, in a cold year and a warm year. And you could get a sense of how much the mixing varies and then how we're able to scale it using a phase diagram and dimensionless indices, kind of like the Hutchinson and Lewis's schemes. Okay, so I'm going to call it a day right there. And if anybody has any questions, or if anybody wants to stay after, if that's possible, I'm more than happy to answer any questions. So I don't hear anything. Is it my sound? Or is nobody talking?
I have a question.
Yes, go for it, Sam.
For that last plot that you showed with the 2-meter deep lake, can you explain more of the mechanisms that cause, so you said that temperature change is often really fast and, you know, the water column homogenizes pretty quickly, but then scalars like oxygen have a more, I guess, slow change over time. Can you explain why that happens?
Well, that's okay. A couple things are going on there. One, the diffusion timescales are different for temperature and dissolved gas, well, solutes. It could be nutrients, it could be dissolved gases. Sam, for you, I should really put in one of our new movies. And I know that tomorrow is not enough. You can't believe how many slides I prepared. Okay, but what you want to remember in those shallow lakes is the wind blows and the thermocline tilts, and the wind relaxes and it goes the other way. So if you have somewhat anoxic water here and you make your measurements at one time a day, you don't see that there's anoxic water below. And then when that wind relaxes, it comes right back. So if I took more time with the isotherms in that figure, it's possible, you know, because we're working with, we've shifted so everywhere we can, we work with instruments with 0.002 degrees C accuracy, which is a lot more than a water temp pro. And that, when you have that accuracy, and that's why if you guys have a budget, you know, like I said, I started with 8 loggers, and then eventually I had more. When you have those good ones, you really can see a lot of processes and you can do a lot of interpretations that you can't when you have the ones that are less expensive. And it's kind of nice. The manufacturers, the really good ones are only 4 times more expensive than the water temp pros. So it's just one of those things. But in short, you've got, in a polymictic lake, you still have this rocking back and forth. And so you can have this cold water pushed over here. And in that case, it was hypoxic or near hypoxic water. And then it relaxes. Does that help? Yeah.
Yeah, thank you very much.
And I do have a slide for tomorrow, if I get to it, which shows a polymictic lake, and it shows the conditions when finally the cyanobacterial bloom can take off, which would also be true then for release of substances from the sediments that they would begin to accumulate.
Cool, looking forward to that.
Yeah, does anybody else have any questions?
I would like to ask a question. I'm Ulrike Oberdecker from Italy, and I would like to ask you, what is the threshold in wind speed for creating internal waves in lakes? Is there any threshold?
Okay, so look, what I'm going to talk about tomorrow is a Wedderburn number and a lake number. And both of those are used to predict the extent of deflection of a thermocline. But in Balbina Reservoir, those internal waves, like even those ones in the subsurface layer, the wind speeds, and I correctly scaled my data to 10 meters height, the winds never went above 4 meters per second. And most of the time we were seeing changes as you went from like 0.5 meter per second to even 2 meters per second. But you have to when you want to think about that, and that's the value of the dimensionless numbers, that deflection is going to depend on the overall stratification. So when you have a super strongly stratified water body, the internal wave amplitudes are very small. And when it's weakly stratified, they can be larger. So you need to know the wind speed and you need to know stratification to really answer your question. Does that help?
Yes. And how is it possible that there are internal waves on the ice?
Well, I'll tell you, this is one of those hotly, no, it's no longer hotly questioned. But when we did a recent paper, we were working in lakes that were only about 2 hectares in size. And lo and behold, they had internal waves. Mm-hmm. And what it is when the wind is blowing across the ice is plastic, or it's a plastic media. And so it feels those pressure fluctuations, and it can have very, very slight deflections, and that sets up the internal waves. The other thing underneath the ice, so I'm not even going to get to some really important terms that we use in physical limnology. There's not time in 2 lectures. But when you have that, the stratification under the ice is actually usually very weak throughout most of it. And so with that weak stratification, even though the deflection of the ice from the wind is fairly small, it can set up a reasonable internal wave.
Okay.
Does that make sense?
Yes, thank you very much for your answer.
Sure.
Okay, we've just hit 12 o'clock, or we've hit the hour mark, wherever you are. I would just like to thank you again very much, Sally, for today's lecture. Freya has been having a bit of difficulty with her internet connection, but just like to remind everyone that we will be using the same link for tomorrow's lecture. So the link that you used today will be the same for tomorrow.
Okay, and guys, remember there was probably I probably prepared 4 times more material than I have time to discuss. So anybody who has more questions, always feel free to write, or ask questions in the chat, but you'll probably need to write to me, okay? Or maybe when we have that next online Leon meeting. All right. Yeah. Okay, so see you tomorrow, and thank you for coming.
Thanks very much. Bye, everyone.
Thanks a lot. Bye.